In the last video, we found the x-coordinate of the center of mass of this volume here with some variable density. And after we calculated the x-coordinate, we said we're done. We already know what the y and z coordinate are. They're both 0. And I really want to double tap into that and explain why that is. So I've already sketched out our volume here. And how I want to show this, let's just try to go through calculating the y-coordinate. So let's try to calculate y bar. Y bar is going to be the definite integral from a to b, and then that's going to be y times dm, and then over definite integral from a to b of dm. And now in the last video, you can recall we said that dm is equal to rho times dv. So filling this in, we're going to have definite integral a to b of y times rho dv, and then over definite integral a to b of rho dv. Okay, and then lastly, we have a few other things we could fill in. So let's apply this here. We said that dv we're going to calculate using our disk method here. So the disk is going to be pi r squared, and we already saw that in the last video. R is going to be this height here. Y is equal to the square root of x. So we can fill this in. Our limits, we said, were 1 to 2, and then we still have this y value that we're going to talk about in a little bit. Rho is going to be 2x squared, and then we said our disk here is going to be pi, and then r is going to be square root of x, and then square that, so that's just going to become x dx. Okay, and then denominator, we can use some of the same information, so 1 to 2 of 2x squared, let's make that neater, 2x squared, okay, and then times pi x dx. Okay, so that's some review from last video, but really, if you can recall to a few videos ago when we were dealing with a very thin metal plate and we were trying to find the y-coordinate of that center of mass, we came into the same problem here. Like, what is y? This is saying that a y position is being weighted with some mass. And what is that y position? And really, we're going to make a similar argument that what we did in that video, but we're just going to extend it to 3 dimensions. So if I were to take another slice out of this volume here, if I were to look at another disk here, and I were to now slice with a plane on an x value. So we're going to get a plane that looks like this, okay? A plane that looks like this. Let's see. Make that as best we can. Looks like this. We're slicing this up with a plane, okay? And then if you were to take your eye, and look at this plane, the x-axis would be, the positive x-axis would be coming out towards you, and this is what you would see. Let's redraw our plane here. Have something like this, okay? And then you would see this disk. Let's make this nice. There we go. Okay, you would see this disk. And if we were to, again, this is the positive x-axis, it's coming out at you, and drawing in our other axes, can label these. We can see that this one is going to be positive y. Grab a little more space. Positive y, positive z, and then negative y and negative z. Now, when we look at this disk, what is our density function saying about this disk? If we were to slice on a constant x value and take this plane here on a constant x value, what is this disk? What's the density of this disk? Well, according to our density function, all across this disk, we're going to have the same density. So we're going to have constant density across this whole disk here. Now, if I were to ask you, remove this volume problem, and I were to just ask you, given this setup here, we have this disk, we could call it a thin metal plate if you want, with constant density. What are, under these axes here, what are the z and y coordinates of the center of mass of this constant disk here, of this constant density disk, this thin metal plate? And you'd say, oh, that's easy. This whole thing has a constant density. That's just going to be at 0, 0. And you'd be right. And that's exactly what our intuition tells us and what this calculation is going to come out to now. So similar to what we made in earlier trying to explain this when we were talking about our thin metal disc, what we're going to end up doing, actually, let's do this in purple. What we're going to end up doing in order to get this y value here, that y position that we're going to weight with some mass, what we're ending up doing is taking an average. We're going to average these 2 points here, and it's going to end up at 0. And same thing in the z direction. You're going to average these 2 points here. You're going to average these 2 points, and it's going to end up at 0. And again, that's a consequence of our density function only varying in the x direction. So if we were to come up here and just make this argument for y, again, we're saying take the average of these 2 points, and what is that going to be? Well, this curve down here, you can say is y is equal to negative the square root of x, okay? And you're going to take an average of these 2 points. What do you get? Well, let's fill that in our integral and see what that looks like. So we have the definite integral. We're talking about our numerator here. Definite integral from 1 to 2, and we said that y is going to be the average of these 2 points here, these 2 heights. So that's going to be the square root of x plus the negative square root of x divided by 2, okay? So that's that y point that we want. And again, that it's going to be 0. So that's what I want you to see. And then we can fill everything else in if we want. So 2x squared times pi x dx. And you can see that this right here goes to 0. This goes to 0. This goes to 0, and therefore everything else goes to 0 in this top integral, and you're going to end up with 0. So you can see that is where that 0 comes from. And the same argument can be applied to talk about calculating the z-coordinate. It's the same argument. And you could draw out these graphs here in the positive z and positive x axis, and you'd have z is equal to the square root of x, and z is equal to the negative square root of x, and you can make the same argument and go through the same calculation. But really, I think the best way to think about it is down here when we drew out a slice with a plane, and we looked at this and we said, oh, there's constant density. You know, what is the center of mass of this disk down here with constant density in terms of the y and the z coordinates? And we said, oh, it's right at this 0, 0 point. So that's really what's going on here. And just a few more disclaimers. Again, this only applies because our density function was only varying in the x direction, okay? When you get into multivariable calculus or something like that, you're going to have different density functions depending on all these other variables here. So this is not necessarily going to be the case. And then also, you can see, we had a volume of revolution, so we had some symmetry that we could use. And that allowed us to apply this, and it's really nice when you have some symmetry and you're finding a center of mass calculation like this.